So first of all, hello everyone. My name is Antonio Garcia-Dominguez, and I am a lecturer from the University of York in the UK. I am not affiliated with Jetbrains itself. I am not affiliated with MPS directly, therefore, not exactly an MPS developer. But I have been using MPS for a while, and I thought I might as well do a training session for MDENet with how do you do model-to-model transformations with MPS. So just let's start with a quick introduction. First of all, what is MPS in the first place? So MPS is short for the Jetbrains metaprogramming system. It's a workbench for creating domain-specific languages, or DSLs. And the interesting thing about MPS compared to something like Xtext is that the programs that you write, well, or the models that you write in MPS DSLs, they're not stored as raw text, like say Xtext, for instance. Instead, you store them as abstract syntax trees. They basically have this whole argument about not needing to use a parser, and that making it much simpler to compose languages. So for instance, if you want to create an extension of Java with a new type of statement that then ultimately gets translated on the fly to some piece of Java code, that's very easy to do. You don't have to go and create an expanded version of the Java grammar and dealing with all the different syntax conflicts and so on, right? You can just define the new statement and that's it. It does mean that the user experience when you're working with MPS tends to be very particular, tends to be quite different to your typical text-based code editing. But over time, you get used to it. The other thing is what is specifically this session about. Just a quick pointer that there was already during the 2022 MDENet Symposium, there was a very good general introduction to MPS from Václav Pech. And he basically did a very broad tour over everything in MPS. Just as a very quick refresher, an MPS project is the basic unit of work in MPS. And an MPS project is made up of languages and solutions. Solutions is where you use the languages to define your models, and eventually you will kick off the transformations from them. And languages, that's where you define your DSLs. And the way they structure a DSL is as a set of modules where you have your structure. That's the definitions of the different concepts that are available in the language, or the abstract syntax of the language, essentially. You have the editors. That's where you define how to present those concepts to the modeler. So that's your concrete syntax of the language. Then you have your constraints and your type system modules. Those provide validation of different kinds and quick fixes and so on. Then you have what's called the text gen or text generation module. So that does the model to text transformation. And it tends to be extremely simple, tends to be very straightforward, very one-to-one kind of model to text transformation. And then the generators, that's where you do your model to model transformations. Okay, so that's where we're going to focus in this session. Okay, we'll specifically cover generators, and I will already have a number of languages that they already have the structure, they already have the editors. Some of them may have constraints, some of them may have text gens. We're just going to focus on the generators because the MPS is huge and we only have about an hour or so, an hour and a half. So how does MPS structure transformations? Generally, it structures them as a pipeline. So say, for instance, that I have a tree model. The tree model goes through a generator module, and that produces a graph model. The graph model goes through another generator module, and that produces a dot model. And then that gets then into actual text that I could use for a compilation process or as an input to some other program. Okay. MPS does have a very strong focus on code generation as the ultimate goal. If you just try to transform a model to another model, but there's no ultimately some kind of text gen generation happening at the end, you won't really get a file out of it. You will get models, and it's possible to get them back and copy them over to your solution. But it's really, really geared towards code generation as the end step. Now, another thing is the natural thing in MPS is that one model produces another model, but you can still produce multiple outputs from a model, but you usually end up having to do a little bit of gymnastics. You have to do either generation plans, or you have to specially configure route mapping rules and so on. So we won't be covering that. There's a link in these slides. And by the way, before I forget, there is, I will just put a link in the chat to the actual slides, because these are available online. So I will just put a link to the slides in a moment, in case you want to follow them on your own page, or if you want to go back and forth. So I will just quickly open the chat, and I will just drop the link to the slides in case you want to go through them on your own pace. And for those slides, you could also follow the links that I have in these slides. So this gymnastics bit is actually a link to a page that kind of explains how to do this. The materials, as I said, these are available from GitHub. I will post the link on the chat as well. I think it's still not ideal to follow these as you go along, because it tends to be a bit clunky. So it's better if you just follow me as I am doing, as I'm sharing my screen. But if later on you want to try this yourself, you can start from the materials that are on the link in the chat. Okay. So the materials that you'll find in that GitHub repository, which I will just open in a moment, you'll find that it has already some languages in there, some solutions, and specifically there are 4 toy languages. I've kept these as simple as possible, so we focus on what do you do with MPS rather than the complexities of the language. So there's dot, which is similar to the GraphViz dot language for describing graphs to be visualized. So essentially this language. It's a heavily simplified version of it, which has its own text generation component. There is a graph language that just has the concepts of graphs and edges, and it doesn't have any text gen. There's one language for describing the structure of a database with tables, columns, and foreign keys, and it has text generation. Not sure if we will be able to go through this one in the given time, but maybe we have some extra time that we can actually go through this one. And there's a tree language, which is just nested tree nodes, and there's no text in. Okay. Specifically, if you want to see the final version of all the transformations, you can switch to the full version tag, and that has the finished version of all these transformations, in case you want to give it a look, or in case we run out of time. So let's move on to the first transformation. Again, these are going to be extremely simple, just to make sure that we can fit them into the time. So the first one is going to be graph to dot. Okay, so the graph language looks like what you can see on the left. You've got graph as the rootable concept, right? So that is what can behave as the root object of a model. And inside you have nodes and edges. Okay, we already have a working editor. We don't have a text gen module. If we want to produce anything really from this, we'll have to transform this language into one that does have a text generation language. Okay, so the target language is the dot language. So you can see an example. You have a directed graph that is the rootable concept, and data contains statements. And statements that are different kinds. You can have edge, graph, nodes, default assignments. So these are the default options for new nodes, new edges, and new graphs. And then there's the edge and node creation statements. Okay, this DSL does have a text generation facility, so it's a good target language, and this is just a very close mapping to the original language. Okay. So if what we want to do is we want to generate text, we could go ahead and try that. And I will now switch to MPS. And I might be going back and forth between these two things, but I'll start switching to MPS now. So the first thing we say is, okay, fine, I have here MPS open, and I've got here my sample input models. So I've got these three, sorry, not these three. I've got this graph, right? I have this graph here that has these nodes and so on. And if, with nothing defined so far, I will try to preview the generated text, and I will get something like this. Okay, so here it says nothing, no text was generated. Okay, that's obvious. I don't have any generators yet that actually end up in any kind of text. So there's nothing for me to preview. So we need to start creating that specific generator. Okay, so what we'll do is we'll have to create a generator. And in this case, we'll just add it as a module of the graph language. So I'll right click on graph, and I create a new generator, and I'll just call it, let's just call it dot to graph, sorry, graph to dot. And I have created that module. And the next thing that I need to do is, because I know that I will have to produce dot objects, I have to make sure that graph depends on dot, right? Which it does. I have made this preparation already, right? But I have to make sure this, because this is how I make available the dot concepts from inside the generator. So I have to make sure that happens. And then the next thing that we have is we have produced this generator module. So that generator module has a generator model. Okay, and you can sort of see that it's a generator model because it has this add generator bit in there. And the next thing that we want to do is we want to just go and open this main mapping configuration. So at the root, essentially the starting point of every generator is this mapping configuration. This contains all the rules that will be applied to transform the input model into the output model. And there's different kinds of rules. Okay, the most common ones that you'll end up using most of the time are the root mapping rules and the reduction rules. These are the most common ones. You'll run into these very, very often. So I'll be using those two to show how to create this transformation. So the first thing I'm going to do is I'm going to create a root mapping rule. And what it basically does is it allows me to create a root element from some object. Okay. So what I do is, and this is where I'll start pressing keys, and it's not entirely obvious because this is MPS. It's a bit atypical. But if I press enter right where I am inside the root mapping rule, I create a new root mapping rule, and I'll say that I want to turn specifically I want to turn graphs into something. Okay. So that's something. I'll have to provide what's called a root template. Now, a root template is basically anything inside the generator model that is not part of the generator language. So if I create here a new, and you'll see here that I do not have here yet available the graph concept. And that is because I also have to list the graph language inside the, the dot language inside the use languages of the generator model. So if I say I want to use the dot language from inside the generator model, I can actually now create a new dot, and I will create this directed graph, and this will be our root template. Okay. This root template, it looks pretty much like a model of whatever concept I selected. In this case, I'll just say generated graph, and I will say that the input to this root template is a graph. Okay, so I say that it's a graph, And I will save these, and let's just try with what we have. Actually, sorry, I defined this root template, and what I'll do now is I'll switch back to the mapping configuration, and I will say that whenever I see a graph, I want to apply these generated graph root template that I have here to turn it into a digraph. Okay, so I will just compile this transformation, and that's another thing that you have to do quite often in MPS. And whenever you make a change, you have to essentially recompile your transformation, because what happens is all this eventually is transformed into Java code, and that's what actually runs the transformation. So if I try to preview the generated text here, I actually get a dot file now, right? It's not a very interesting dot file, but it does show that the whole transformation is happening, okay? Now, obviously, we have to go on and fill in all the details, but we have that starting point. So what we're going to do now is we're going to populate that root template a bit more, so it's closer to what we actually want. And that's another thing where MPS is quite different from your typical, say, ATL or ETL model-to-model transformation languages. It's essentially template-based rather than rule-based entirely, like, say, ATL. So I start filling this up. I say, fine, I want to add a new statement. Let's add a node creation statement, right? And I say, let's just call this node n. And then I'll just add an edge creation statement, again, as an example. And let's say that for now, I'm just going to put some placeholders here, and it's an edge that goes from n to n, right? So if I do this, of course, I can still make, I can still preview, I get the new output just fine, and so on. But again, not particularly interesting. This is a fixed output model. So let's keep going. Now, if what you want to do is you want to make this template actually dynamic and actually compute the output nodes and so on, you have to use something called macros. And you have node macros, you have property macros, and you have reference macros. Okay, the way you create this is you select the node in question that you want to compute on the fly, or the property in question whose value you want to compute on the fly, and so on, and you use Alt-Enter to trigger an intention. And I'll just show now as an example. So what we'll do is let's just copy the objects into the output. So what I'll do is I'll first select this statement, and I'll say that I want to, another thing to show, you may be seeing that you can see the keys I'm pressing whenever I'm pressing modifiers, because some of these interactions are not obvious. If I press Control Up, I will select the parent node to where I am. And if you keep doing that, I'll keep selecting the parent node of the AST. Okay, you have to be very aware that you're working with an AST when you are developing MPS model-to-model transformations. So what I'll do is I will wrap this with an node macro, and particularly it's going to be a copy source L over the nodes in the graph. Right? So I'll say that I want to do this, and I'll explain what this means in a bit. And so this is essentially what it's going to do is it's going to copy the nodes from the graph into the dot model, but it's not going to be a straight copy. It's actually going to reduce, or it's going to transform those nodes that they're going to copy, right? I will do the same for the edges, right? So what I do is, again, I select the edge creation statement as a whole, and I say this whole thing is actually going to be wrapped by a copy source L macro, and the input to that macro will actually be the edges. And that's also another important thing to say in MPS. And I don't know if you may have noticed this, but it's very important to keep an eye out for the inspector that you have at the bottom right, because in many cases, depending on where your editor cursor is on the editor, your inspector will change. So for instance, if I put my editor cursor inside copy source L, you'll see that it's now giving me options for this particular macro, right? So I'm saying this particular copy source L is going to be using the nodes of the graph, and this other one is going to be using the edges. Okay, so always keep this one open. If at any point you close it or if you don't see it, it's right here at the bottom right. It's very small, but it does show this inspector bit here on the bottom right. Okay, it's very important to keep it open when you're working with the MPS. So now that I have that, the next thing is to say, okay, fine, but how do I actually transform these nodes and these edges to something useful, something that actually belongs in this module? So for that, what we use is something called a reduction rule. And a reduction rule, what it does is, again, it transforms something on the input model into something on the output model. So here I'm going to say that I'm going to turn nodes into something, and this something I have to specify. So there are multiple ways to do this. In the case of what we're going to do, we'll use what's called an inline template. So I'll just create what I need straight from here, straight from this mapping configuration. And I'll do control space, and I'll say that I want an inline template. Okay, so these inline templates will produce something, and that something will basically replace the node, the original node. Now, how to press control space again to actually select what I actually want to produce. And this, I have to remember the type, okay, of the thing that I want to produce. So say I want to produce a node creation statement, and that now gives me a little sort of inline editor of the concept I'm editing. So again, we start with some placeholders. So nothing too particularly interesting here. So these would basically just create this fixed node creation statement all the time. But obviously, that's not particularly interesting. We want to actually have these nodes have the name of the original graph node, right? So what we're going to do is, again, with the cursor, the editor cursor straight in the end, right before the end, I will press Alt, Enter, and I will say that I want to add a property macro. And this property macro essentially allows me to customize the value of the property whose value I was seeing. So here in this editor, I was seeing the name of the node that was being created. And what I'll do is I'll just add this little expression here inside the macro that says that actually that should be computed from, sorry, the name of the node. Okay. So with that, I will be computing the name of the node, and so far so good. Let's say that we want to add another reduction rule, because we did the one for the nodes. Now we want one for the edges. And again, the way to do this in MPS is I put my cursor right after the last reduction rule. I press Enter, and that gives me another reduction rule. And in this case, I want one for edges. Okay, so I want to turn the edges into something. And in this case, I'll say that I want specifically an edge creation statement. And that edge creation statement, as usual, we start with a bit of a placeholder, really, just to give us, slots to put values in. And what I'll do is I'll say that it's going to be an edge that goes from, let's say, n to n. Okay. It doesn't really matter what we have here because we're going to replace it anyway. Now, one thing that happens here is obviously, these, I don't want to just have ends, right? I want to actually refer to the node that was produced from the source of the edge. And here I want to refer to the node that was produced from the target of the edge. So I need to, actually replace these values. Okay, these values that you see here, these are actually references to existing nodes, right? They look like text, but they're really references. So what I need is to use reference macros. But exactly what I put in here, that's the tricky part, right? So I can say I want a reference macro for this one, and I want a reference macro to replace this one. But what do I put in here, right? Because what I want here to put in this reference expression is, please give me the node that was produced from the source of this edge. Okay, I need to do that. The way to do that in MPS is through something called equivalent mapping labels. I'll just switch quickly to the slides, right? So mapping labels, if you've used something like ETL or ATL at all, it's essentially it's tackling the same problem as equivalent. Okay, it's basically the same problem. And the way to use a mapping label, you have to follow 3 main steps. You have to define the label in the mapping configuration. You have to ensure that there are some rules that create that association that actually populate the mapping. And then you have to use that label from the gen context object that is passed to a macro. And I'll show how that is done. Okay. So I'll switch back to MPS and I'll show how to do it. The first thing that we want to do is we want to define this mapping label. And in this case, I'll call it the same as in the slides. So I'll say graph node to dot node. And this mapping label, again, it just says, from this particular concept, this other particular concept was produced. Okay, so I say that from a graph node, it produces a dot node. Okay, I'm just doing that. So the first bit is defining the mapping label in the mapping configuration. The next part is actually populating that mapping. And the way to do that is you need to go to wherever you're producing that node in question, and you have to say, please add this to the mapping label. So the place where I'm actually creating the nodes, the dot node, is from inside this specific template inside the node reduction rule. So what I'm going to do is I'm going to put my cursor, again, be very mindful of the AST, the underlying AST. I'm going to put my cursor right there before the N. I'll press Alt Enter, and I'll say that I want to add a node macro. Now, this node macro is, again, wrapping the node that is inside this node creation statement. And I'm going to use the label macro to assign the current source node, which is a graph node. And I'm going to say that that graph node turns into this node, the node that is being created from inside here, right? This actual node that is being created. Once I do that, then the next thing I can do is to use that label. And I'll say that now I go back to the reference macro that populates the source of the edge. And I'll say that I want, from the gen context, please give me the output by label and input in question. So the label is graph node to dot node, and the input node is going to be the source of the edge. Right. So in this case, node is the edge in question. Yeah, as in it's node because it's the S node of the model, right? It's a bit confusing, but it's the way that it is in MPS. So I have that part done, and I can do the same thing on the other side. I will do gen context, get output by label and input, and I'll say graph node to dot node, and I'll say in this case it's the target of the edge. Okay. So once I do that, I'm almost done. There's just one extra bit that I'm just going to do, because we do have cases where we might actually have, say, multiple graphs being produced and so on. I'm just going to tweak the root template to tweak the name of the graph. So, it's not always the same name. So I'll just add a property macro around the name of the graph. And I'll say that it's going to be based on the name of the graph, okay, of the source graph. So once I do that, I will just close everything else. I will compile the transformation. And now that I have the transformation, I can preview the output, and you'll see that we produced, the diagram, and it has all the things that we wanted. Okay. One thing that is very useful, and I'll just quickly show it, is something that MPS has, which is called transient models, because it allows you to see the different steps that things go through. So it really helps when you're debugging. Okay. Now, if you want to enable the tracking of those, there's this, again, very little thing on the bottom right. I don't know if you may be seeing this T off thing way on the bottom right of the screen where I'm moving my cursor. You see that very, very tiny thing. If you click on that and it turns on, when I regenerate, I'll just make the project again and I'll preview again. Now I can go to this part way at the bottom of the logical view, which has these transient models. So this allows you to go through all the steps of the transformation. And you can see that we started from this graph model, and we ended up with this directed graph model. And this is what actually got produced, got turned into text. Okay. It's also very useful because you can also do things like I can right click on this N4 node, for instance, and I can use language debug and then show generation traceback to find out exactly how it was produced. So I can say that this particular N4 node in the graph, right? I can say that it went through this reduction rule, and particularly this bit where the node was created, and it turned into this thing, right? So that can be very useful when you're debugging a long chain of transformations, and at some point you say, why was that generated and why in that way? You can find exactly which rule was applied to produce a specific model element. Okay. So this is the first example transformation that I wanted to go through. I just wonder, any questions from the chat before we move on? Anything that is unclear? I haven't seen any questions in the chat. So either everyone is following along or everyone is very lost. Okay. So if there are no questions in the chat, I'll keep going. So now I'll go to another example. This is a tree to graph. Okay, so again, it's quite a simple one. Didn't want to make it too complicated, but it does show some extra bits of MPS. So tree to graph. So I have this tree language, which is extremely simple. I only have one concept, which is called tree. And it's essentially just a recursive tree, right? It has a label, and then it has children. If you think about it, it's essentially like a more restricted version of the graph DSL. Now, one thing that would be nice is, because we already know how to turn graphs into dots into text, if we just turn trees into graphs, then we could reuse that. Okay. So that's very nice. We'll be doing that. And I'll be showing one thing that you can do, which is you can use a separate generator-only language to try different approaches, right? So if you say that you have one source model, but you want to try different transformations for the same source model, you can do this by, again, separating and saying, I'm going to separate the language that provides the concepts and the syntax from the language that provides the actual transformation. And it can be quite useful to do this. So we're going to start by creating one generator language, which is going to be called tree to graph .reduction. And I'll just go back and do that. So I'll close this one and I create a new language. So in this case, I say new and language, and I say that I have tree to graph .reduction, and I create a language. Okay, so I have this language. Now, languages by default, they do come with a generator, which is fine. And again, this is not going to have any structure, right? No editors, no structure. It's just going to have a generator. What I'm going to do is, because I want to transform tree to graph, I need to make sure that the language in the dependencies, it extends both tree and graph. Okay, so I have to say I want tree, I want graph, and I want to extend both. Okay, so that's the first bit that I want to do. And what I'll do now is I'll create a new root template. Again, I have to make sure that the generator model uses the target language in there. So I'll say that I want to use graph. And I'm going to create a new root template. So here's a graph. And I have to say, well, what's my input? What does a typical graph look like? I do the same usual thing. So I say from a tree, I want to do something like looks more or less like this. Right? So I have my node, and I have an edge. And again, this is just placeholders. Doesn't really matter what I have in here. It's just I have a place to put in macros and so on. Okay. So I have this fixed graph. And now I'll have my root mapping rule. So my root mapping rule, very similar to what we did before. We say that we want to take a tree and we want to turn it into a graph. Okay. Now, the thing that's a bit different is we do have to specify a condition, because these root mapping rules, in principle, they go through any instance of tree. They don't care whether the tree is a root or not. Okay, they in root mapping, as in they produce roots, but the inputs can be, they don't have to be roots. So I have to limit this root mapping so it would only apply to root trees. So I'll press enter while my cursor is in that condition slot. I press enter, and now I'll say I only want you to map the cases where the node in question does not have a parent. Okay, so if it doesn't have a parent, then I actually produce that. Okay, now I'll make the language and I'll just try to turn this tree into something. And you see, oh, no text was generated. What's going on? Now, that is because the way in which MPS selects the generator to be applied, it usually, what it does by default is it uses the generators of the languages that you have inside the model. So the tree language does not have a generator, so there's nothing to generate. If I want to, if I want to use something that is not part of the languages that are used in the model, I have to actually tell it explicitly. So I have to go to the model properties of the input model, and I have to tell it, hey, I want to use this particular language, generator of this particular language, right? So it has to be listed when I'm using the generator of a language which I am not using. I'm not using any of its concepts in here because it doesn't have any. I have to explicitly tell it. I have to tell it I want to use this generator. Okay. So if I do that, I can preview and I get the transformation. Okay. So far so good. Obviously, we need to add some templates and so on. So we'll make it a bit more interesting now. So let's switch back to the root, template. I will need some bits. Okay. So actually, we need a bit more. We need another placeholder node, because I'll need also something to be a placeholder for the root of the graph, and then the root of the tree, and then I'll need something for the descendants of that root. Okay, so I select the root and I add a node macro, and I say I want to copy just the root. Okay, so actually I don't have to do anything because I am already, this template starts from the root of the tree. So that's it. I can just use the current source node as the map node. Okay, because this one is working with the root of the tree. And then for this one, I want to use a different macro, which is the copy source L. And you may notice actually the difference, right? So copy source doesn't have an L. L is for list. So copy source just copies one node. copy source L copies a list of nodes. Okay, and in this case, it's going to be just the descendants. It's going to be the descendants of this root, and particularly the descendants which are trees, which they all are, but I need to do something so it's type safe. Okay. So, okay, that's fine. Obviously, we will need to add these reduction rules as usual. Okay, and we can define that reduction rule as normal. So I will just go and define it in a moment. I'll go here to the reduction rules, and I will say that a tree turns into a node. Okay, so I will say that I want an inline template, and I will say that I want a node, and particularly I want a graph node, and the node is going to be called after the label of the node in question. Okay. Nothing too particular. I'm just turning one thing into another thing. And now the next thing that I want to do is I want to populate these edges. Okay. The problem is we can't really use copy source again. We can't use copy source again because you only get to reduce a node once, and then that's it. Right? Because essentially reducing nodes, it replaces them in terms of the input. It's, if you're familiar with things like term rewriting systems, it's the same kind of idea, right? You're basically replacing one thing by the other. You only get to reduce a node once. So we have to do something else. For that something else, we're going to use a different macro, which is called loop, and it's quite useful. And I will loop. So, instead of using these loop macros over specific things which are not useful, I will just loop through a particular expression I will define. So I'll just type loop in here, and it's a loop macro that essentially what it does is I provide this iteration sequence, and I will say that I want to loop over the descendants of this root. Okay. Because so what I want to have is just have essentially a child pointing to its parent. Okay, I want to do that for everything, every hidden node in the tree. So what I'm doing now is I will loop over the descendants of this tree, and for each one, I will try to evaluate this little part. Okay. Now, obviously, we do need to use reference macros as we did before to replace the values of these two references in the edge. But again, we need a mapping label for this. Okay, so let's just go and do that. We need to do the same thing as before. We go to mapping label. Let's say that I want to turn a tree. So let's call it tree to node. And it tracks from a tree the node that I'm producing from it. Okay, so this again is defining the mapping label. And what I'm going to do next is I'm going to go to, I need to actually populate the label. So besides the label macro, there's another thing, which is many rules, they will also have mapping labels. So in this case, because I'm producing from a tree, I'm producing a node. Instead of having to do it inside here, I can just do it from here. I can just do it from the rule. So from the reduction rule, I will specify the mapping label, and I will say tree to node, and this will also populate the mapping label, right? So this will take a tree, it will produce a node, and it will tell tree to node, hey, I produced this node from this tree. Okay. Once I have that, I can use it in a reference macro as usual. So I can go back to the that root template that we had, and I can say gen context, oops, context, and this is, so gen context is an object that exposes a set of methods. One thing you'll notice in MPS is that methods may not look like your typical Java methods, because again, since they can extend Java however they like, they will sometimes use like, special syntax just for that. This will be mapped to Java in the end, right? But, it doesn't look like Java when you're actually calling it. So what we want to do again is I want the output variable on input, and I want tree to node for the source of the edge. Oops, actually the source of the edge, yes. So we want to do child to parent edges. So the source is just going to be the node, which in this case is a tree that I'm going through inside the loop node. And then in the case of the target is going to be the parent. So I use get context, I use get output by label and input, I have tree to node, and in this case, I use an operation that's called ancestor, and it's essentially the opposite to descendants in a way, right? So if I say that I want the parent tree, I want the container of this, I will do node ancestor concept tree, right? So in this case, what it would do is it will find the first tree that contains this one, and it will return that. Okay, so this is giving me just the parent tree node. So once I have that, I will compile the language, and I will run the transformation, and I get the node. Sorry, not this one, not this one, this one. Okay, so let me just go and do this in a moment. Hold on, I'll just do this again. There we go. So we get these two graphs, right? So it transforms each of these two, and we can actually see in the transient models, we can see that we started from these two trees. These got turned into these two graphs, and then these got turned into these two directed graphs. Okay, so you can see the whole chain that eventually produced those files. Okay, one thing I did miss, which I have to do in a moment, is to customize the name of that generated graph, because it's not particularly great. They're always the same name. So I'll just add a property macro, and I'll say that I want to produce I want to give it the name of the root of the tree. Okay, I just want to tweak that in a moment because it's a bit ugly. And I'll make this, I'll preview the text, and there you go. You have this one and this one, and you can follow through the transient models the journey that I went through, right? So you can say this one and this one. And in fact, if I have a chain, one thing that's nice is I can say this T3 that I have here, if I do my traceback, I actually see the whole chain. So I say, okay, so in this phase, you had this graph, and that I apply this rule and this node creation statement to produce this bit, right? So this is the graph to dot phase, but I can go even further back, and I know that this T3, I apply this rule, this particular node creation bit, to produce this one. So I can follow again the whole chain of transformations from end to end. Okay. And as you see, not always you can get away with just reduction rules. Sometimes you'll need, say, loop rules and so on. Okay. Let's see. Just having another look of the chat. I don't see any more questions in the chat either. So if you want to ask anything about this one, feel free to drop a message. If not, I can just move on to the other ways to do this. Okay. So essentially, we have two options now, and I guess it depends on what the audience wants. We can either just work through recreating this transformation in other ways using other concepts in MPS, or I could go through a more complex transformation and just essentially walk you through the code, but it's already made. Does the audience have any preference? Okay, I don't see any preference. I might as well just work through other ways to write this transformation that exist, okay, just to show other concepts that exist in MPS. So let's go through other options that we have. I'll just basically say that I don't want to use this reduction language anymore to transform the tree to graph, and let's just try other ways to do it in MPS, okay? So the next way to do this is through what's called weaving. Okay, so weaving is a bit particular. Weaving, what it allows you to do is to insert nodes at arbitrary places of the output model. Okay, so it's not so much you apply a template, is you apply a template, you generate something to start with, and then later on you insert new nodes into that output model. Okay, so I just wanted to show you, that there are multiple ways to do the same thing in MPS. So let's just create a new language. I'll just go back and create a new language for this. And let's say that I create a new language. Let's call it tree to graph weaving. And in this case, I'll say that we have as dependencies the same as before. We have the tree and we have the graph languages. We both select the extent, and we have those two languages available. And we also have to say from the model, the generator model, that we want to use the target language, which is graph. And we do the same thing. And now I'm going to create a root template, same as before. And now I'm going to call it tree. I will do the same thing about generated graph. I will, let's say, call it the same for now. Nothing too groundbreaking yet. But the interesting thing is I'm going to leave this empty. Right? I'm going to leave these completely empty. I'm not going to add any nodes. I'm not going to add any edges here. Okay, that's a thing that's going to be different. We're going to add them later through weaving rules. So we have to define some weaving rules for that. And the way to do that is you define something called a weaving template. Okay, and I'm just going to create that. It looks very similar to a root template, but it's slightly different. I'm going to create inside the generator. I'm not going to create, say, just a plain object. I'm going to create something, a template declaration, okay, which is a bit different. So in the template declaration, I give it a name. So I want to weave a tree into a node. Okay, the input is going to be a tree, as before. And now for the content node. Now, the difference between a root template and a template declaration is in a root template, you want everything. You want the whole thing, right? You want to put everything in here into the output model. In a template declaration, you don't want everything that is produced from this template. You only want certain bits. Okay, that's the main difference, really. I'm still going to start with a graph. Okay, I'm going to give it some names, but the idea is I'm going to create just enough to give me a placeholder. And then the bits that I actually want to sort of extract from this template, those are going to be wrapped in what are called template fragments. I'll just go through the motions a little bit and then I'll show you. So say that what I want to do is I want, whenever I'm weaving a tree into a node of the graph, what I really want to do is produce a new node, okay? This is what my template fragment is going to be, right? That's essentially what I want to do. For every tree, I want to weave a new node into the graph. That's what I want to do. So I'll do that. One thing I will have to do, of course, is to customize the name of the node. And we'll do that as usual, right, through a property macro. And another thing that we know we're going to need is we're also going to need a mapping label for the same reasons as before. Okay, so we need a mapping label that goes from the tree to the node. Okay, that's exactly the same. So I'll just go and advance more quickly through that. I want that. And I will also add this node macro with the label. And I want the tree to node. Okay, so I have these. Fine, I have that weaving template, and I'll just compile, right? So this is fine. This basically says, from a tree, you produce a node, and we'll see later how we actually add this node, which is between these TF tags, how we actually add that back into the graph, okay? So we have one for nodes, And let's add another one for edges in this case. So in this case, I'll create another template decoration. And I say that I want to weave trees into the edges of the graph. And I will say that my input is going to be a tree again. My content node is going to be a graph again. I'm going to give it some name. It's a placeholder, doesn't matter. I'll add a node. Again, name doesn't matter. That's a placeholder as well. And I want an edge. And this edge is going to also have placeholders in them. That's actually going to be my template fragment, because this is what I want to produce from this weaving template. I want to produce edges. Okay. So now I'll need some reference macros. So the same thing we've really been doing so far. So gen context, get output by label and input, and we have the tree to node, and the node is the source of the edge. And we'll do the same thing for the other one. I will say gen context, get output by label and input, tree to node, and then node, and I want to find the tree that contains this one. Okay. I want to compile this again, which will also remove that red squiggly that we had on top of the graph, because we didn't, you hadn't noticed that we had added this template fragment. So that's good. But we now have to actually tell the mapping configuration how to use this. Okay. So what we'll do is we'll go to the main, we'll go to this main mapping configuration, and we'll add these weaving rules. So you see that there's this weaving rules section. And what you do is you say, well, I want trees to be woven this particular way. So I want the weave tree into node. And there are two ways to do this in the slides. I'm doing it in a certain way. I might as well do it in a different way for this demo. So say that I want to do a weaving rule for the case when the node is a root. So when the node is a root, what I want is I want to get specifically the graph that was produced. So sorry, I need to slow down a bit. So we said, fine, we want to take the trees which are roots. We want to apply this weaving template, but we need to say, where are we going to add the things that we have created, right? So we say, fine, this weave tree into node, that's going to produce a new node. Where do you want me to add this node exactly? Okay. So that's what's called the context rule. I have to tell it where to put the thing that I created. Okay. What we need in this case is we need to get the graph that was produced from the root of the tree. Okay, that's where we want to add the new node. We could use a mapping label. That's perfectly possible, but I'm going to show another way in which you can do it, which doesn't need a mapping label. Okay, so what I'm going to say is gen context, but in this case is get copied output for some node. And that's going to be because this is actually the root tree, it's just itself. Okay, so this copied output, this is basically the output that was produced for a given input. Now, because I have, I did forget to do this, sorry, I did forget to do this. I do need to define the root mapping rule. Oops. So let me see. Sorry, just give me a moment. Give me a second. All right, hold on a moment. Bit of a, let me see. Okay, so I'll just share my screen in a moment again. Okay, I'm sharing my screen again. So I've got this root mapping rule. And in this route mapping rule, I will apply the generated graph template. So again, let's return to what we were doing. So what we have done here is from the root tree node, we want to produce this graph according to the root template. And then from the root tree as well, we want to apply this weaving rule, this weaving template, and we want to add it to the graph that was produced from this root mapping rule. Okay, that's what we're doing. Okay. Now we do need to do the same for the the inner nodes. So in this case, I'll say, well, when you are not a root tree node, when you're not the root of the tree, I still want to apply the same templates, but in this case, I want the copied output from the ancestor. So actually, sorry, not ancestor, but ancestors. I think it's ancestor. Hold on a second. Actually, yes, ancestors last. There we go. Right. So I want the copied output for the last ancestor, which happens to be the root of the tree. Okay. So once we have that, if I haven't forgotten any steps, I will go to the test inputs and I will go to the tree. I'll just make sure that I've got the right. Nope, I don't have it here. So I need to tell it to use the weaving language. And I'll just make sure to close everything. And I will also make the project because it's saying that it needs generation. And then I'll preview. And okay, oh, yes, of course, we forgot to add the weaving rule for the edges. So I'll just add a weaving rule for the edges. And for the edges, I want to do trees that are inner nodes. And then I'll do weave tree into edges. And I'll do the same thing. I'll apply actually the same context code as before. Because again, I want to add it to the graph that was produced from the root of the tree. So I do the same thing. I'll compile this transformation. And if I preview the text, I do get the edges. Okay. So this is the other way in which you can do things. You can essentially start from a root template and try to do everything from, kick off everything from there. Or you can generate something and then later you can add some weaving rules. This can be useful sometimes when you have a language that is going to add a few concepts, and then you want those concepts to weave things into other things, but without actually going through a root template and so on. Okay. Any questions so far about this? No, don't see anything in the chat. Okay, everybody's really quiet. That's fine. I assume that's a good sign. So I'll keep going then. Right, so we have done weaving. There's another type of rule that we can apply, and that's the last type of rule I was going to introduce in this, and then later on, if we have any extra time, we can go through some more advanced transformations. Okay, so the next one I'm going to do is one type of rule called a conditional root. So a conditional root, they allow you to create a new root from scratch instead of mapping an existing root. Okay, so for instance, imagine that instead of producing one graph per tree, you wanted to create one graph that has all the trees together, right? So if you want to do that, a conditional root is ideal. And to save some time, what I'll do is to copy tree to graph reduction and then just modify the minimal bits that we did to speed up things along. So I'll just create, might as well make before I do any big changes. I'll create the language and then I'll duplicate things. Okay, so I'll first create tree to graph conditional. I'll do the same thing as before, where it's going to extend those two, the input language and the output language. So it's going to do that. But in this case, I'm just going to delete the main mapping configuration, and I'm just going to copy over the ones from deduction, because there's really not a lot that I have to do this. So I'm just going to do that. Okay, so I copied over the rules from the reduction example. And what I'm going to change is, instead of using this root mapping rule, I'm going to delete that. And I'm going to say that I just want to add a conditional root rule that says that I always want to produce that graph, that generated graph. Okay, I always want to produce that one. Of course, in this case, we don't want to compute, we don't really have an input to compute from. So I can remove the input from the template. Like, templates don't need to have an input, actually. And I'm also going to remove this bit. Okay. And I do need to change some things in this template. So in this template, obviously, I'm not going to start from a root. So I will have to just delete this bit. I have to go and just copy over everything that was in the model. So what I'll do is I will I will change the map nodes in this copy source L to only to just include all the trees in the model. And I can do that from the gen context. So gen context, I can ask it for the input model, and then I can ask it for all the nodes of a certain type. So I just want to go through all the trees in the model. Right? I just want to reduce all the trees in the model. And in the case of loops, I can do the same. I want to go through all the, let me see, I want to go through the trees. But obviously, I actually only want the ones that have that are inner nodes. So one way I can do that is I have this where operation where I can define a filter, and I can say where IT, sorry, let me just make sure. Right, yes, I did have tree where IT parent is no. Okay. I have this one, I have this one. I'm reducing and going through both. And in theory, we should be done. You'll see that we get a bit of a warning about things when I try to apply this. And I've had to make some tweaks to avoid that warning. But to be honest, I don't think it should be necessary to do that. There may be something in MPS that myself am not fully understanding. But I'm going to say I want this conditional node, and I'm going to preview this generated text. And oops, we did miss one thing. Okay, let's go back. For node ancestor concept tree, conditional generator. So this one's fine. This one is not fine. Right? Let's see. Sorry, we wrote this the wrong way. Let me just fix this in a moment. Right, we wrote this the wrong way. And there we go. Okay, so with these, what we do is, instead of turning every tree into a graph, we produce one graph and then we put everything in it. Okay, that's something else that we can do. One thing, I guess, again, that you will notice is we have these warnings about multiple outputs being produced for certain nodes. This is one aspect that, as I was developing this example, the last week, I wasn't entirely sure why I was doing this. It doesn't seem to, really have any issues, and it does seem to produce the right outputs, but it just happens to be interesting. If you want to avoid that warning, and a warning is triggered from here because when we are asking for the output of a mapping label for a given input, there is the implicit assumption that there is a single output for this label and input, right? If we can't really be sure of this assumption, then what we might want to do is say, okay, fine, let me just give me the list of by label and input. And then I'll just take the first one. Okay, and we can do the same thing for the other case, where I can say I want the get output list by label and input. I have a tree to node, and I have my for node ancestor tree first. And if we do that, and then I preview, I close, and I preview, then it's fine. Right? That avoids the warning. Not entirely sure why this is happening in this case. It's something I would need to poke a bit more into the innards of MPS to happen, to be honest. Okay, but that was pretty much the last type of rule that I wanted to really go through. In total, we've used route mappings, conditional routes, reduction rules, weaving rules. We've used multiple node macros, copy with reduce, label, looping. We've used property macros, reference macros, mapping labels, and you may have seen a lot of alt enter control space. Okay, which is the thing that it takes some time at first in MPS to just make sure that you've got your editor cursor right in the right place, and you know where to press enter, where to press control space, and where to press alt enter. Okay, that's the one thing that gets a bit tricky to get used to at the beginning. We missed a lot of MPS. There's accessory models, there's utility classes, dev kits, generation plans, doing language extension, the many other kinds of rules, pre and post processing scripts, template switches, and so on. If we have the time, which we might, we could go through the object-oriented to databases transformation. But in this case, we can just browse through that if you like. Okay, so sounds good. So in that case, I'll just go quickly through that. So this one is already made. Because I wasn't going to. There was no time to actually go and create it. Within the hour that we have. But this transformation, basically, what it does is I'll just quickly demo it. So I have this O entity, and I'll preview. And that's. Oops, I do have to tell it to use it. Hold on a second. I just want to demo it quickly. Okay, so I'm just going to do that. Okay, I'll close all. I'll just do this. So what it does is it takes these Java classes that are just plain Java classes. They just have fields, okay, of different types and so on. So it's a very simple data model where I have a school and I have people that have some contact details, and then I have students who are people and they have a grade, and I have teachers who are employees, and the employees are people who have an address, they have some students, and so on and so on. And I also have groups of students, and so on and so on, right? And from all that, what I do, I'll just have to close everything again and preview again, is I create this SQL database schema. Okay, this is something that you can go and paste into SQLite, and it works, right? So the way this is done is these Java classes, they're actually using the base language in MPS. So the base language is essentially Java. It's pretty much Java. Right? You just write Java. Again, what you see here, it looks like text. It's not text. It's an AST. If you try to edit this, you'll get a very different experience to your typical, editing with an IDE. But it looks like Java language, and I do have this SQL language that has some basic concepts around databases. And you can see an example here. This is what a model looks like, right? So I have this database that has invoices and customers, and then I have my columns. I have some constraints, and I can say that a particular column is a foreign key to the ID in another table, okay? So this SQL DDL language has its own text gen model. So you'll see here that I have ways to produce text out of these models. So what I really want to do is I want to map these Java classes into these databases, right? I want to map essentially these into this. I want to do a transformation. So these object-oriented to database transformation language. So this one actually, it does have a concept because and that's interesting. So one thing that happens in this transformation is I need to provide a mapping from, say, Java types, like, say, string. I need to map that to a SQL data type, okay? One thing that I've done is the SQL DDL language. One thing that's interesting in MPS is that languages, they can come with models, with some like predefined instances. So SQL has this concept of a data type, right? And that data type, it's essentially, your varchar, your int, your big int, all these data types that you get in databases. And it also comes with a model, a utility model that comes with the language that already defines some of the most common SQL data types, right? So this already comes with the language. Now, because this already comes with the language, I can also use the data transformation. I can say, well, I'm going to define a concept in my transformation language, which is actually a mapping from this Java type to this SQL type, right? So this is a concept that is for this transformation. And I have what's called an accessory model. And the interesting thing about an accessory model is this is not available to people, right? This is just to help me specify the transformation. So my accessory model says, hey, you should map strings to n varchars. You should map integers to ints. You should map booleans to bits, and you should map big decimals to numbers. These are actual models. They have references. They will check for referential integrity, and they will complain if something got deleted and so on. But I can use these as an input to my transformation, right, which is quite powerful actually, because it means that if I want to add a new mapping, I can just go and add it right here. Right? I can just go and add it here very quickly. Now, this transformation, when we go to the main nitty and gritty, it looks very similar to the kind of things we've done. So we've got our mapping labels that map from the Java class to the table associated with that class, from the Java class to its primary key, and from a field declaration to a value, to an actual column that stores that value, okay? We have a conditional root rule that will always produce a certain Java database, the basic structure. And if you look at this, you say, okay, where's everything else, right? So in this case, I didn't end up with that many reduction rules. I ended up using essentially all these loops, right? And it gets a bit tricky to go through everything. But the interesting thing is, I've got a loop to go through all the classes in the model. And I've got another loop that goes through the many valued fields. So for instance, when a teacher has multiple, I'll just show this bit. When a teacher has multiple postcodes, right? It's this part of the root template that produces tables for all the postcodes of that teacher, okay? And what you can see here, and I'm using the same things mostly that we have seen, right? I've got things to produce the primary key of the table. I've got things to say if this Java class has a superclass, I can create a foreign key to the table of its superclass. So I essentially do one table per class. In terms of inheritance, I'm populating my mapping labels to keep track of which field gets turned into which column. And there are slightly, there's this thing that I haven't shown yet called a switch that allows me to, depending on some conditions on the input node, I can decide to apply this template or this other template. Okay, so if I actually go to this switch, This says if you have a field decoration and it can be mapped to a scalar SQL data type, apply this particular inline template. But if not, then apply this other template. Okay, because if not, then this is actually going to be a foreign key to a row in another table. Right? So I can use switches for this kind of thing. I can use different conditions to decide between different templates that I want to apply. Okay. Then there are more bits here, but most of these should be pretty much familiar to you. It just gets quite a bit more complicated and a bit finicky because of all the expressions and so on. But if you want to go through these at your own leisure, it's pretty similar to the things we've done. One thing that is different is, and you may notice, I don't know if you have this bit for instance, right? You might notice in this loop, I am actually calling this class called mapping manager, and I'm saying, mapping manager, please give me the parent fields of this node, right? So this method, actually, this class doesn't come with MPS. This class, it's part of the transformation action. So you can have Java classes, Java utility classes that help you with particularly complicated parts of your transformation. You'll see that in this generator module, not only I have a generator module, generator module, I have the generator model that is accompanied by this utility module that actually has these Java classes. So these are Java classes that come with the transformation and that I can invoke for particularly tricky bits of the transformation. Or when I end up having the same code in multiple places, I can extract it to a utility class and I can call it from here. That's one very useful application of these utility classes, because I noticed that I kept running into the same code in different places in this transformation. And I said, I'll just refactor this into its own utility class. The other thing that I have done that is different in this transformation is I've used something called a post-processing script. So a post-processing script, what it does is it allows you to, and pre and post, right? So there may be cases in which some of the things that you want to do with the module, they're not very naturally expressed in MPS, right? And you actually need like a bit of imperative code to do this. So if you need to do something to the input model before it goes through the rules, you can apply a pre-processing script to do that, okay? And I've seen that, for instance, when you have like a library of functions and the pre-processing script basically just copies over the function from the library into the program, right? I've seen other languages do this. In my case, I'm not doing that, but I am post-processing the output model in a certain way. And what I'm doing is I'm actually sorting the tables. Because one problem that you see very often when you're generating SQL is obviously the order in which you put the create statements is very important. Because obviously I cannot put, say, this at the beginning, right? Because SQL wants the person table to have been defined. And it wants the teacher table and the group table to have been defined, right? So this is very important, but it's not very nice to specify in MPS by itself. And that's why I use a post-processing script to do that. And what I do is I say, MPS, after you've done your transformation, just put it through this processing script. That processing script is here. And it just basically uses this class called table sorter that I have in the utility class, and it will sort the tables according to that. Now, that table sorter, it's a Java class that can do whatever it wants. But in this case, I'm basically doing all these things about computing the closures based on foreign keys and sorting tables based on that. And if they're the same according to the closures, I'm sorting them by name and so on and so on. So this is something that I can specify pretty easily in Java, but doing that in MPS will be very, very painful, right? So what I do is I use a post-processing script to do this, okay? And that's pretty much it. That was the more complicated transformation that I wanted to show. And I think we've just about run out of time, I think, Nuno.
Yes, pretty much, Antonio. Thank you very much for this presentation. It was wonderful. I would just like to leave a small survey in the chat, as always, for us to assess how these sessions are going and what people feel about them. Thank you very much, Antonio, and all of you for being here with us today. Looking forward to seeing you in our next events. Thank you very much.
Okay. Thank you all.
Bye-bye.
Goodbye.